Hey, Geometry, Lesson 21. We're going to talk about right triangles and some special relationships we have within them. Let's just get into it. Okay, first, let's look at these triangles right here. Are the triangles shown above similar? Explain. Okay, we should know how to find out if things are similar or not to this point. We have a few rules for that. The rule we're going to use here is angle, angle. If you have two congruent angles in a triangle, then your triangles can be similar. So I just did, let's show you my work. 180, goodness. Minus 90, minus 56.3, and I got 33.7. So we know that this angle is congruent to that one, and this angle is congruent to this angle. And, in fact, this angle is congruent to that angle. So the two triangles are similar because of the angle-angle theorem. So let's write that down. So because of angle-angle, the triangles are similar. Both triangles have a right angle, and the measure of angle A is equal to the measure of angle X, and the measure of angle C is equal to the measure of angle Z. Determine the unknown lengths of the triangles. If you remember back to the last few lessons, we just set up some ratios to determine that. So first of all, let's assign some variables. First of all, let's let X represent YZ. Go ahead and put it in blue. Let's go ahead and set that up. So I can say 3 over 2 is equal to x over 1.5. I can do that a few different ways, but this is the way I'm choosing to right now. I'm going to do some cross multiplication and get 2x is equal to 4.5, so x is equal to 2.25. Okay, let's try another one. Let y be the length of the hypotenuse of ABC. I'm just going to put y right there in red. Let's set up another ratio. Actually, with that one, I can do the Pythagorean theorem, can't I? Let's do that. Okay, 2 squared plus 3 squared equals y squared. 4 plus 9. 4 plus 9 is 13, so y equals the square root of 13. Cool. Now let's look at the other unknown side, and let's go ahead and label this one z. And I'm going to do Pythagorean theorem again, since we know what x is now. 2.25 squared plus 1.5 squared equals z squared. Okay, 2.25 squared, 5.06. 25. 1.5 squared is 2.25. Okay, let's add that up. I get 7. Oh, goodness. Sorry. Oh, I can't erase it now. Okay, 7.3125 equals z. So square root of that. A little bit messy, but you got it. Okay, this question is asking how we found the lengths in part A. I believe what it's asking is, like, how did we find x? Because part A of this question, we didn't find lengths. So when I found the first unknown, okay, I used ratios. And I could have used ratios for the other unknowns, but Pythagorean theorem is pretty simple. So for part A, I used ratios. I guess that's not for really part A, but to solve for x, I used ratios. Then to solve for y and z, I used Pythagorean theorem. Okay, example 1. Recall that an altitude of a triangle is a perpendicular line segment from a vertex to the line determined by the opposite side. In triangle ABC below, in triangle ABC to the right, BD is the altitude from vertex B to the line containing AC. How many triangles do you see in the figure? I see three right triangles, to be perfectly honest. Identify the three triangles by name. It's funny, they ask you and then they tell you the answer. So there's lots of ways to name the three triangles, so I'm going to try to name them to show some corresponding angles. So I have a right triangle there too, and I'm going to try to name it like short side, long side, hypotenuse. Let's see if that'll work. First, that little triangle. I'm going to start at A, go to the short side, and then over to the long side and make sure that goes back to the hypotenuse. I just went short side, long side, hypotenuse. Okay, let's name the other one. Let's go for the super big triangle. I'm going to go short side, long side, hypotenuse. Triangle A, B, C. So I just went short side, long side, hypotenuse. And then that last one, I'm going to do that again. Short side, long side, and back to hypotenuse. So I went short side, long side, hypotenuse. Remember, the hypotenuse is always the side across from the right angle. So lots of ways to name those three triangles, but I just tried to pick some that would show some corresponding angles. Okay, if we notice that angle A is always going to be equal to angle A. What else do I see here? Angle C equal to angle C. Angle D equal to angle D. I think that's all I see, but pretty cool. Okay, we want to consider the altitude of a right triangle from the right angle to the hypotenuse. Okay, the altitude of a right triangle splits the triangle into two right triangles, each of which shares a common acute angle with the original triangle. In triangle ABC, the altitude BD divides the right triangle into two subtriangles, triangle BDC and triangle ADB. These are all the triangles we named in the previous slide. Okay, is triangle ABC similar to triangle BDC? Let's do that one first. Okay, ABC and BDC are similar because of the angle-angle criterion. Okay, if you see, hold on a second, I have angle C, I have to rewrite these so make it bigger, ABC, similar to triangle BDC. So all we're looking for is angle-angle. I already have C in the same place, so those are congruent. And then each triangle has a right triangle. Let's highlight it for us. We have ABC, A, B, C, okay, B being the right triangle. And then we have BDC, BDC, angle D being the right triangle. So yes, these are similar because of the angle-angle criterion. Okay, let's try the other one. I'm going a little slow on this because I want to make sure that we all understand it. Oops. Triangle ADB. Okay, we see that I have A in the same spot, so those are congruent. Now let's look for that right angle. ABC, ABC, B is my right angle, and then ADB, ADB, D is my right angle. So yes, they're similar because because of the angle-angle criterion. Cool. Good job. Okay, let's look at ABC and DBC. So we have ABC. B is my right angle. And DBC. DBC. Okay, for this one, D is my right angle. So let's mark that. A, B, C. I have to write that bigger. A, B, C. Where we had B was 90 degrees and triangle DBC. Where here I had D was 90 degrees. ABC and DBC. Okay, these are congruent, but those B's are not. Let's see, ABC and DBC. Okay, so no, these aren't similar. Corresponding angles aren't equal. Bummer. Okay, since triangle ABC and triangle BDC and triangle ABC and triangle ADB are all similar, can we conclude that triangle BDC is similar to ADB? So we have ABC similar to DBC, ABC similar to ADB, and so can we conclude that those are similar? Yeah, we can. Similarity is transitive. Similarity so those being similar to the same triangle says that they are similar to each other. So we can say triangle ABC is similar to triangle BDC is similar to triangle ADB. Very cool. Identify the altitude drawn in triangle EFG. Okay, the altitude, pretty simple. Oh, that's huge. Hold on. Did not mean to do that. There we go. Much better. GH. Segment GH is the altitude from vertex G to the line containing EF. Alright, so as before, the altitude divides the triangle into two subtriangles, resulting in a total of 3 triangles, including the given triangle. Identify them by name so that the corresponding angles match up. Okay, so I'm going to go, this time let's go ahead and go like hypotenuse, short side, long side. Just to show you we don't have to do everything the same way. So EF is the hypotenuse, and up to the short side and back to the long side. Okay, now let's do the medium-sized triangle. Let's see, the hypotenuse. I'll do EG, so that's the nope. Sometimes it's hard to see, so I'm doing this one now. Yep, there's the hypotenuse. So EG, H, E. Okay, let's do the little triangle now. We're going to do hypotenuse, short side, long side. The hypotenuse looks like GF, and then short side, and then long side. GFH. Cool. Okay, next slide. Okay, yes, the altitude does divide the triangle EFG into 2 similar subtriangles, just like the one with ABC. And altitude is always going to do that. That's sort of the point of today's lesson. Okay? Alright, the fact that the altitude drawn from the right angle of a right triangle divides the triangle into 2 similar subtriangles, which are also similar to the original triangle. Okay, we're going to use this to determine the unknown lengths of the right triangles. We're going to set up some ratios and solve some triangles. Right, so consider the triangle ABC below. Draw the altitude BD from vertex B to the line containing AD. This would be BD. Label AD as X, and label DC as Y, and BD as Z. Cool? Now we're going to work to find the values of X, Y, and Z. And if you see right here, this is the drawing I'm going to use for the next few slides. It's just labeled a lot better than what I did over there. Cool? So make sure your drawing is labeled well so we can work with it. Okay, we're going to try to muscle through this and then show you an easier way. So notice I just wrote the similar statements up here so I can compare some sides. Let's see, if I compare triangle ADB, which is the first one, to triangle ABC, I may be able to get it. So ADB I'm just going to put some similar sides on top of each other and set up a ratio. So AD is X over AB is 5 is equal to DB. Nope, I don't know DB. I can't use that one. Dar. That's not going to work. Oh, let's do AB. The little triangle AB is 5. The big triangle, so I just went AB, is AC, which is 13. Awesome. So what I just did was AD, which is X, over AB, which is 5, is equal to AB, which is 5, over AC, which is 13. Let's do some cross multiplication. 13x equals 25. X equals, I'm just going to leave that as 25 over 13, which I can simplify to 1 and 12 over 13. Messy, but that's correct. Okay, let's try another one. Let's see. Let's try to find y this time. So y, I'm going to compare triangle BDC with triangle ABC. Let's see, do I know BD? Okay, that's Z over, so I just went BD over AB is 5. Let's see, what else do I know? AC, BC. Oh, I know BC. It is 12, so I just did BC over AC, which is 13. So I have 13Z equals 5 times 12. Darr. Divide both sides by 13, and I have Z equals 60 over 13, which simplifies to 4 and 8/13. Messy. Okay, let's try to find y this time. You following me? Let's see, y is BDC also. BDC. Yeah, that's what I'm going to do. Especially since I know Z now, even though it's yucky. A, B, C. So, let's compare. So I'm trying to find DC, right? Right there. That's Y over BC. Is 12 is equal to BD. No. BC. Oh. into BC over AC. Okay, cross multiply, 13y equals 144. Divide both sides by 13. 144 over 13, which simplifies to, this is y 11 and 1/13. Okay, that was sort of messy. Do you guys agree? I could have used Pythagorean theorem that at the end. Once I have two sides of a triangle, I can find the third side pretty easy, but my mind was already going on ratios. That's sort of what I went with. Okay, let's see if we can figure out a somewhat easier way to do this, because I was not a fan of that one. Okay, we're going to look at a different strategy for determining the lengths of x, y, and z. The strategy requires we complete a table of ratios that compares different parts of each triangle. So here we have our table, and I have the same triangle drawn there again. So we're just going to do some ratios. If you look, I'm just looking at like shorter leg to hypotenuse of this triangle, etc. So let's try to fill it in. For triangle ABC, that's the big one, ABC. So let's look at our shorter leg is 5. Our hypotenuse is 13. Longer leg is 12. Hypotenuse is 13. And then shorter leg is 5. Longer leg is 12. Okay, keep going. So ADB, I've got my shorter leg is X. Hypotenuse is 5. Longer leg is Z. Hypotenuse is 5. And shorter leg to longer leg is X and Z. And then CDB, I've got Z and 12, Y and 12, and Z and Y. All right, so we've got this table now, we're going to use it. All right, so our work in example 1 showed us that triangle ABC, triangle ADB, and triangle CDB are all similar. Since the triangles are similar, the ratios of their corresponding sides are equal. For example, what we just did, we found the value of x by setting up that ratio, okay, using the similar triangle statement. Okay, that's how we found x. So that's what we're going to use to determine, or we're going to use these ratios, which are set up in a table now, not just my messy handwriting, to determine the values of the other variables. Goodness. So we can use the ratios because the triangles are similar. Similar triangles have ratios of corresponding sides that are equal. And we know we can use ratios between figures or within figures. So this one is within figures. So x over 5 is 5 over 13. When I did it, I used it between figures, and it worked out just great, right? So let me write down this answer so you can write it down. So we can use these ratios to determine the length of x because the triangles are similar. Okay, and that's what we've learned in past lessons. So which ratios can we use to determine the length of y? Let me bring that table back in here. So to determine the value of y, we're going to look at the values of the longer leg and hypotenuse for triangles CDB and ABC. So these two. I'll go ahead and circle those. Right? So we're going to go ahead and try y over 12 is equal to 12 over 13. And this is exactly what we did earlier. So we've got 13y equals 144. So y equals 144 over 13, or 11 and 1/13. Okay, what I didn't do when I did this example the first time is we could have used Pythagorean theorem. Also, okay, once we have two sides of a right triangle, we can use that to determine the third side. How about to determine the length of z. There's actually lots of ways. I can grab these two and go, or I can grab these two and go. Okay, I probably don't want to go here because those are two unknowns. But I can go 5 over 13 equals z over 12, which is 60 equals 13z. Or I can say 12 over 13 equals z over 5, which was this one. 60 equals 13z. Okay, lots of different ways. There's actually two more ways, but that's all right. So basically, there's lots of ways to solve for z. So since corresponding ratios within similar triangles are equal, we can solve for any unknown side length by equating the values of the corresponding ratios. In the coming lesson, we'll learn about more useful ratios for determining unknown side lengths of right triangles. Okay?